Today, I'm going to talk about wall warts. These are the power supplies that come with various pieces of electronic equipment. And the question is, if I have a wall wart that is made for one device, can I use it for another device? Today I'm going to tell you how to find out. Let's begin with the two most important parameters, which are voltage and current. So let's assume that the plug fits, that both the power supply and the device are either AC or DC, and if they're DC, the polarity is the same. And just to simplify things, let's assume that the power supply is regulated. So let's say you went to a garage sale and you picked up a nice Casio musical keyboard, and it did not come with a power supply. So you go to your drawer full of old wall warts and see if you can find a match. So let's say the keyboard says it is 12 volts DC at 1 amp. And you find a wall wart, ready to plug it in. Plug matches. So let's see, it's 12 volts DC and 2 amps. Well, yeah, there's a problem there because everybody knows it's the current that kills, not the voltage. The keyboard says it needs 1 amp. This says I'm going to give you 2 amps. So that's going to push 2 amps into the keyboard and it's going to fry it, right? Wrong, especially assuming that this is regulated. What this is telling you is the keyboard says, I need 12 volts DC and I'm going to take 1 amp of current. This says, I can give you that 12 volts DC and I have plenty of current to give you. I can give you up to 2 amps. Take all you need. And the keyboard is only going to take what it needs. So when it comes to choosing a power supply for a device, especially if the power supply is regulated, you want to match the voltage. There could be some leeway there, but you really want to match the voltage. But when it comes to the current, you want the power supply to have equal or greater current. And it doesn't matter how much greater, especially if it's regulated. Yeah, oh, that going to really fry that? Of course not. The keyboard's only going to take 1 amp. And so that is a perfect match. Now, if it's not regulated, there could be a problem, and we'll talk about that in a minute. But the bottom line is that if it's regulated, and how do you know if it's regulated? Well, modern power supplies are often switching power supplies, and those are always regulated. One way you can tell is if you look at it, it says it's a switching power supply, but even if it doesn't, if it's very lightweight for the power it gives, then it's probably a switching power supply, because unregulated power supplies tend to have big, heavy transformers in them. And so if you have a 1 amp supply that's huge, it's probably, it may or may not be regulated. But if it's tiny, it's almost certainly regulated. But look on there, and if it says regulated, or if it's a switching power supply, or if you open it up and you see there's a lot more than just a rectifier and a filter, then it's probably regulated, especially if there's a chip in there of any type. So once again, if the power supply is regulated, match the voltage, but don't worry about the current. As long as this is equal to or greater than the current demand, it's going to be perfect. This will not push too much current in there. This will only take what it needs. Now let's take a closer look and see how these circuits work together and give us a little more information about how to choose wall warts, especially if they're unregulated. Let's see what happens here. Let's take a look at the equivalent circuit for what that power supply is. So we start out with a battery with a resistor in series with it. So Thevenin's theorem says that any circuit that produces an output can be reduced to act like a single voltage source with an impedance in series with it. We are reducing that even more by making the voltage source a simple battery instead of some AC source, and the impedance is just a resistor. So our power supply acts as if it were a battery and a resistor in series. Now, if this is regulated, all bets are off as to what's going on over here, because this is going to skew what happens, and the regulator is going to monitor the output voltage, and no matter how much current I take, it's going to keep that output voltage constant. So when I go to the device that I'm powering, and anything that consumes current can be represented by a single resistor. So let's take a look at what we had there. That was 12 volts and 1 amp. So what's that tell us about that? Well, it tells us what this input impedance actually is. 12 volts and 1 amp. If we want to know what that resistance is, we divide the voltage by our current. So 1 goes into 12, tells us this is a 12 ohm impedance here. So our input impedance is 12 ohms. Therefore, our circuit acts as if it were a 12 ohm resistor. Now we're going to deliver 12 volts to that. So the regulator is going to hold that at 12 volts no matter how much current is going through the regulator. So 12 volts no matter what, 12 volts, 12 ohms, 1 amp. So if it's regulated, it doesn't matter what the capacity is. So we said that was 12 volts and 2 amps. The regulator is going to hold that voltage the same no matter what current goes through it. And we see this acts like a 12 ohm resistor with 12 volts. We'll have 1 amp and nothing's going to change. So if we have a regulated power supply, all we have to do is match the voltage and make sure that the power supply has equal or greater current. But what happens if it's unregulated? Let's erase some of this here. Erase the regulator. And now see what happens. So what does this tell us about the power supply now? Since it's not regulated, this information tells us, well, it doesn't tell us everything because we know this voltage source has to have some overhead. So it's going to be higher than our output voltage. Let's make it 15 volts just because it is. So now this is saying that I will have an output of 12 volts when my current is 2 amps. So current of 2 amps, output of 12 volts. I start with 15. I'm down to 12. That means I'm going to lose 3 volts across this output impedance of my power supply. Well, now I know I'm going to have 3 volts between here and here. 2 amps going through that. I can calculate what that resistor is. So 2 goes into 3. That's telling me that that is a 1.5 ohm resistor. Let's erase this clutter. And that's 1.5 ohms. Now we couldn't tell that about the regulated power supply because we had other circuitry that obscured that. But since it's unregulated, now we can calculate that out. So our power supply is acting as if it's a 15 volt battery with a 1.5 ohm resistor in series. Now our device acts like a 12 ohm resistor. Let's see what happens when we hook these together. So here is our entire circuit once we hook them together. So this says 12 volts DC at 1 amp, but all that tells us is that it's a 12 ohm impedance. This says 12 volts DC at 2 amps. It tells us that, well, we had to speculate about this battery, but it tells us we're going to have some higher voltage. Let's see what happens if it's 15 volts. If it's a higher voltage, things will be a little different. But let's just take a look at this. So what do we have? A simple series circuit, 12 ohms, 1.5 ohms series circuit. So we simply add those together to get our total resistance. So that's 13.5 ohms total. Now we need to know what our current through the circuit is, and we can calculate that by using Ohm's law. So the current is going to be our voltage divided by our resistance. So pull out my trusty calculator. 15 volts divided by 13.5 ohms gives us a current of 1.11 amps. So we can already see that our current is higher than the device wants. What's the output voltage? Well, now we have 1.11 amps going through 12 ohms. And if you want to know your voltage, you multiply. So 1.11 times 12 equals 13. Let's draw that in red so we can see it over here. That gives us 13.32 volts. So if the power supply is unregulated, we notice that we do have an increase in voltage and an increase in current. Not the whole 2 amps, only 1.1 amps. So is this going to work out okay? There's a lot of latitude in how much voltage we can put in a lot of circuits and how much current they will take. this is probably not going to be a problem whatsoever, especially if it's something that's designed to plug into a cigarette lighter in a car. Your car battery, it says 12 volts, but it's really 13.2 when it's fully charged. When it's charging, it's going to be 14 to 15 volts. So yeah, this is well within something that's designed for that. And there's usually plenty of latitude. So just a little extra current, a little extra voltage, probably not going to be a problem at all. Let's see what's going to happen if this is a much higher capacity power supply. So let's erase our parameters here. Let's say that is a 10 amp power supply, unregulated. Could have a problem here. Give us a little more overhead here. 10 amps, yeah, we'll see. What's that tell us about that resistor? Well, 18 volts, 10 amps, that means we're going to be down to 12 volts here. So there's a 6 volt drop across this resistor when there's 10 amps flowing through it. So what's that resistor going to be? 6 divided by 10 equals, that's going to be a 0.6 ohm resistor. Now let's see what happens as it is hooked up this way. This still looks like a 12 ohm resistor, but now our power supply looks like it's 18 volts and 0.6 ohms. Let's erase this clutter here. So that's 12.6 ohms total and 18 volts. How much current are we going to get? That's 18 divided by 12.6. That's going to give us 1.4 amps. Yeah. That's half again what this wants. Let's take a look at what the voltage is going to be. That's 1.4 amps times 12 ohms equals 17 volts. Yeah, let's put that in red because we did before. That's 17 volts. So yeah, if we have a much greater capacity than our device wants and we have an unregulated power supply, we could have a problem here. So if it's unregulated, you don't want to go too much higher over here. But we saw that if it was only twice the current, it wasn't that much. So once again, when you're choosing a wall wart to go with some device you bought, match the voltage and the wall wart should have equal or greater current capacity. If that's twice the current capacity and it's unregulated, probably no problem, maybe even 3 or 4 times. But if you get to a huge difference in capacity, you could have a problem. So you don't want to be using an unregulated power supply that's designed to supply a lot of current to something that doesn't want a lot of current, because we're going to get an over voltage and an over current. And this is probably enough to, I would be very, it depends on the latitude, but 17 volts, 1.4 amp, and we want 12 and 1 amp. Yeah, I wouldn't want to do that. Just for the fun of it, I recalculated this using an 18 volt battery, giving me a 6 volt overhead instead of a 3 volt overhead, and came out, once again, 12 volts, 1 amp, acts like a 12 ohm resistor, and I came out with 14.4 volts across the device and 1.2 amps. So the voltage went up a little bit, current went up a little bit more. We're probably still okay. Once again, I said that there's a wide latitude on the voltage things can take, and if this is made to plug into a cigarette lighter, that's well within what it's expected to be able to take. So even if we have a higher overhead, this is probably more realistic than the one I was using, we're still not that much higher than the demand is. So we're probably still okay even with an unregulated power supply, as long as this is not too much higher than that. So that's twice the current capacity. I think we're still good, but we get to even higher current capacities, then we have to be careful if it's unregulated. But regulated, we're just fine. Now let's see what happens if we go the other way. Let's change our ratings here. Let's say this is 12 volts DC and it wants 2 amps, and our power supply gives us 1 amp. Let's see what happens when we do that. Let's erase our numbers here. And let's go back to the 15 volt battery just so we are working with the same original idea. So As a matter of fact, why don't we keep this the same? Keep that at 2 amps. And let's say this wants 4 amps. This might not be as realistic, as far as power supply, as far as your common power supplies and common devices, but I just want to show what happens if we want more current than the power supply can deliver. So 12 volts DC, 4 amps. It was 1 amp, now it's 4 amps. So what's going to happen? This is going to end up being a 3 ohm resistor. So 4 goes into 12 3 times. So now our device looks like a 3 ohm resistor, and we're back to this, which looks like a 1.5 ohm resistor. So now our total resistance is going to be 4.5 ohms. And to find out how much current we get, we take our 15 volts, divide that by 4.5, and that gives us 3.33 amps. So our device says it's 12 volts DC and is going to demand 4 amps because it's only a 3 ohm impedance. Already we see, no, we're not going to get that 4 amps because this says we're going to be 3.33 amps. Let's see what happens to the voltage over here. So we have 3.33 amps, multiply that by our resistance, and that gives us our voltage, which is 10 volts. So we are losing a full 5 volts across this. We could actually calculate that out because we have 2 amps, so actually it's 3.3 amps and 1.5 ohms. Calculated, it's going to be about 4.99 some odd volts because these numbers are not exact. But yeah, we're going to lose 5 volts down to 10 volts. So if we demand more than the power supply can give us, our voltage is going to go down. And this is even true of a regulated power supply. That's why I drew that with, let's put our regulator back here just to have that circuit again. The regulator is going to give us a constant voltage because basically the regulator looks like this. It's another resistor. Now, of course, it's more sophisticated circuitry, but it acts as if it were a resistor in series that is variable, that adjusts to keep the voltage constant regardless of the current going through it. But when this gets down to 0 ohms, we still have 1.5 ohms left. And so if this is a regulated power supply, we still have a maximum. Well, it's still going to act like this circuit when we try to take too much current. So we got above our 2 amps, and the voltage starts to go down because of this series impedance in the circuit. So if we demand too much, we're going to have our voltage begin to sag on the output. That's just the way circuits work. It's like if someone tries to take a shower and flush the toilet at the same time, you're trying to draw more water into the house than the pipe coming into the house can deliver, and something's got to give. It's going to be the pressure. Same thing's happening here. If I'm trying to take more current than my power supply can give, something's got to give, and that's going to be the voltage. So if you take less current than the unregulated power supply is rated at, you're going to get a higher output voltage. If you take more than any power supply is rated at, you're going to get a lower output voltage. So that's the nature of how that works. Now let's take a look at some other things we may need to know to match things up. One is the polarity. Well, first of all, if they're both AC or both DC. So if it says 12 volts AC and the other one says 12 volts DC, that's going to be a problem. Now, it might say 12 volts AC, might say 12 volts DC. It also might say 12 volts and have a little tilde next to it, a little sine wave telling you that it's alternating current. That sine wave may be somewhere else, maybe down here or something. DC, it may say 12 volts DC, or it might say 12 volts and have this symbol, a solid line with a dashed line above it, or that might be somewhere else. But this symbol means DC, and this symbol means AC. So you have to make sure that they're both either AC or both DC. Now, if they're both DC, now we have to look at the polarity. And the polarity symbol looks like this. It's a C with a dot in it and 2 lines coming from those. This represents the power plug. Now I'm assuming that you're using a coaxial power plug that looks like this. If it's not that, then, well, if they don't fit, they don't fit, and that means you're going to have to go to Radio Shack. And yeah, Radio Shack's not dead yet. There are some stores with Radio Shack sections that you can buy such things, or go to Amazon to get the parts you need. That you might have to do some soldering and fix it up, and that's a little beyond what I want to talk about. But let's assume that we have a coaxial connector, and that coaxial connector goes into a jack which has a little springy connector on there and a pin, and the jack looks like this. Little black plastic insulator there, and if we look at the end on, we have a central pin and an outer conductor, and that's made so that the jack or the plug goes into the jack and slides onto the pin and connects up to this spring metal and slides onto the pin. Now, there's a lot of latitude for the diameter of the plug itself, but the diameter of the pin has to match the hole that is inside the plug. And those are different sizes. Now, my experience is that devices that have higher voltages have a smaller pinhole, which makes it difficult to plug into a jack that's made for lower voltage. But that's an observation I've made of just a few devices. I wouldn't quote me on that because I don't know if there's any truth to that or not. But that could be a way to safely prevent a high voltage device from plugging into a low voltage device, because if the high voltage device has a smaller pinhole, then it won't plug into the lower voltage devices that have a bigger pin. So does it fit? If it fits, you're in luck. And then we have the symbol where this represents the outer conductor, that represents the pin, and usually you will find this positive on the inside, negative on the outside. That's called negative ground because the ground is the lowest voltage in the circuit, and that's connected to the outside. If it looks like this, these need to match. So there is a positive ground, and those are incompatible. I once bought a little portable TV at a swap meet, and it was a positive ground system, and it was 12 volts, 1 amp, positive ground, and I had plenty of wall warts that were 12 volts, 1 amp, negative ground, and I could have just simply cut the wire off and swapped the wires on the power supply, but instead I thought, you know, I can use this with most power supplies because usually things are negative ground. So I actually went into the TV and cut and spliced on the circuit board to convert the TV to work with this connector. And I scraped off the plastic where this was molded onto the plastic and rewrote it with a Sharpie to indicate that the polarity had been changed. So there's your polarity. Those have to match. So to reiterate all the things we need to know, you buy something at a garage sale that doesn't have a wall wart. It has a coaxial connector. You have wall warts with coaxial connectors. First thing, does the connector go in? If it fits, step one is good. Check the polarity. Make sure that they're both the same polarity. Negative ground is the most common, so you look at the symbol on both the power supply and the device and make sure that matches. Then you look at the voltage. Look at the voltage of the device. And then look at the current. Now look at your power supply. Is that good? Well, probably, even if it's unregulated, that's probably okay because this isn't much higher than that. If it's regulated, it's perfect. Doesn't matter what the current is. As long as the current of the regulator is greater than the demand of the device, then this will work, especially if it's regulated. Doesn't matter how much higher the current is. If it's unregulated, if you suspect it's unregulated, you might not want to go more than 2 or 3 times on the current because you will get a higher voltage and a higher current on the device. But once again, regulated, you're in business. So check the polarity. Check to make sure that they're both DC or both AC. The power supply has to have a current capacity equal to or greater than the device, and only have to be worried about how much greater if they're unregulated. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.